We said this is a good, starting this example problem is a nice stopping place for the previous video. So that's what we did. Work an example. I'm going to write the givens down here, and then I'll go full screen with the camera so you can see it. So we've got a weighted piston cylinder, contains 0.3 kilograms of steam. Steam tells me that's water. Right? So some problems will say it's just steam. That tells me my substance is water, not necessarily in the liquid form. In fact, they're telling me it's going to be in the superheated vapor form by using the word steam. They've given me the mass, 0.3 kilograms. They've given me a pressure, that appears to be an initial pressure, 1 megapascal. They've given me an initial temperature, 400 degrees C. Determine the boundary work if, and they've given me a final state here. So the pressure is still 1 megapascal and a final temperature of 250 degrees C. And they want me to find boundary work, which out of just habit, I'm going to compute that in the out direction. Now there's one more there's one more given here that they've told me. It's not a number. I had to figure this one out based on what they've told me in the problem statement. And here's where I would wait for somebody in class to tell me what it is. That might be a minute, that might be 20 minutes, but I'll wait patiently until them go back and look at their notes. So that's kind of what I'm doing at this point. I'm stalling just a little bit to give you a second to figure out, all right, what's the one thing that is given, but we've not written down over here. I know it's a little small for you to see. Go ahead and pause, figure this out, right? This is important. Okay, do you think you have it? The biggest thing is, what are the adjectives telling me? This adjective right here, back, that tells us something. Always know what your adjectives are telling you. That tells you your pressure is constant. That's important. Let's talk about why that's important. Why that's important. Well, what am I trying to do here? I'm trying to find the boundary work. Now, what I would do in class is I would say, okay, well, what's a good tool or path or we talked about fundamental problem solving. And fundamental problem solving is, what are you looking for? What do you know? Right? What's known? All right, what are some good tools or laws or equations or relationships or paths to this solution? What are some good tools I had to find this? Well, anytime you've got an unknown energy, the first law is not a bad place to start. The first law will let you find an unknown energy, but it will only let you find one unknown energy. Now, this problem has not said anything about heat transfer. And I know in chapter 2, I said, well, if they don't say much about heat transfer, you can probably ignore it. But after about basically chapter 4 and beyond, we won't be able to do that. Well, here we are. This is chapter 4 and beyond. We can't just assume there's no heat transfer unless they tell us there's no heat transfer. So if I wrote the first law equation, I would have heat transfer and I would have boundary work out. And then I would have m delta u, which we'll see that in a little bit. So in the first law equation, I would have two unknowns. I wouldn't be able to solve the first law equation. So if I'm looking for boundary work, yes, you can write the first law equation, and sometimes that's how we will solve the first law equation for an unknown boundary work. But I would always suggest to you, if you're looking specifically for boundary work, also don't be afraid to explore the definition of boundary work and see if you can solve that. Right? So by definition, the boundary work is equal to the integral of pressure with respect to volume. Now there's two pieces to this. I've got to know the limits. I need to know the initial and final volume. Those are unknowns. Then I also need to know how pressure changes as a function of volume. That's an unknown. So I've got three unknowns here plus the boundary worker. I've got three things I got to work with here, right? I need to know how pressure changes as volume changes. I need to know what these two limits are. And the one thing I'm looking for. So this is the only thing this needs to be the only thing I solve for. I need to be able to figure out the rest of this out. Okay, well, do I know how pressure changes as volume changes? Yes, that's what I told you earlier was important. They told you how pressure changes as volume changes. So since P is constant, since P is constant, then the boundary work out is equal to, then I'm going to pull the pressure out of the integral. This is the easiest integral. That's going to be integral from V1 to V2 dV. All right, hopefully that sinks in a bit. And then how do I do this? Well, then I just need to integrate with respect to V. Integral of dV is just V. Integral of dx is just x. So this is just P times whatever V is. Well, I'm going from V2 to V1. Okay. If that doesn't mean anything to you, like you have no idea what I've just done, I really need you to go back and focus on your calculus because you are behind at this point about a semester or two. Okay. So at any rate, I'm going to assume you know what that means and we're going to keep moving. If not, go search the web for learning how to do single variable integrals in calculus. Okay. Okay. So what else then? Well, I know pressure, that's known. Pressure's known. I need to know these volumes. How do I find volumes? Well, anytime I'm trying to find an unknown property, I need to know what my substance is. My substance is water. Okay, my substance is water. I can use property tables for water. I need two properties at each state. I need to know state one and state two. I need to know two properties at each state. Well, I know P1 and T1, and I know P2 and T2. So I know two properties at each state. I should be able to find specific volumes. So total V2 is going to be mass times specific V2. And total V1 is going to equal mass times specific V1. And table properties will lead me to these two. So far, so good. Or I can also, if you like, I could say boundary work out is equal to MP delta little v. Either one is just fine. Right? That's an or. Right? Another way, I think a lot of times the textbook will tell you also, because mass is constant, you can pull the mass out of this term, md little v, and then the mass is constant, so it comes out of the integral, and now I've got mp integral d little v, and this becomes just delta little v. You can do it through calculus also, but you can see here I'm just pulling this common mass out of those two, and which is a known quantity. So I know the mass, so that's known. So all I got to do now is find these two unknowns, and we can solve. So I'm going to make another block down here for properties. Properties. All right, given P1 and T1, I should be able to find V1. And given P2 and T2, I should be able to find V2. All right, I'm going to share screen here. I kind of played with trying to put a textbook in front of us here to do this, and that's only marginally worked. So I'm just going to go to the property tables. Now, I'm going to assume that you know at this point how to, given a pressure of 1 megapascal and given these temperatures, figure out that you're going to be in the superheated phase. If we were in class, I'd take a little time, make sure we kind of brush up on that. We've already covered chapter 3. We've already covered property tables a little bit. So that now becomes a smaller part. Using property tables becomes a smaller part in a bigger problem. Initially I've got 400 Celsius. So at state one, the specific volume is 0.30661, and the units there are meters cubed per kilogram. I know you can't quite see that on my screen here. I'll go back to full screen in just a second. I got to get these properties first, though. State two, it goes down to 250. So again, these are from the Changle and Bowles text. I'm using it for education purposes. I'm not monetized on this channel. This is the specific volume at state 2 based on those two properties is 0.23275. That's according to the 6th edition of the Changle and Bowles text. You'll find the water property tables most likely have not changed in the newer versions. If they are, feel free to leave them in the comments. If you're using another text, you're going to get slightly different properties, but probably within 2 significant figures, we're going to agree, probably 3, maybe 4, just depending on what models they're using. We don't know exactly which models they're using in this text. These are just what they're recommending to us. Now, I can go on to the next page, or I've got room over here. I'm just going to say the boundary work out equals, you know what? I am going to go to the next page. Go on to the next page. Lecture 8, page 3 of something. Boundary work out is going to equal, we said earlier, that is mass times pressure times the change in specific volume. So the mass, according to our givens, is 0.3 kilograms. Our pressure is 1 megapascal. And our specific volume then is V2 is 0.23275 minus V1 is 0.30661. Both of those are meters cubed per kilogram. So the boundary work out then is going to equal up. Let's see what I'm doing. Okay. So 0.3 times 1 times quantity, 0.23275 minus 0.30661, close parentheses, equals, and I get here a value of 0.0, it's negative, by the way, negative 0.022158. And then we look at our units and say, well, kilograms go away. I've got megapascals, meters cubed. And again, the rookie mistake is to say, Steve, it's the metric units. Doesn't it just work out? No, that's a terrible assumption. If you're careful, yeah, they normally do work out. I don't know if you guys remember, but we had previously done our units kind of off to the side. We'll go through it quickly here. If I've got pascals times meters cubed, a pascal, of course, is a Newton per meter squared, and that's still times the meters cubed. So a pascal meters cubed is, I've got here, this is Newton meter, which is a joule. So this is megajoules. What I've got here is megajoules. Boundary work out. So if I take everything down to base units, normally they do work out. What I've really got here is minus 22.16. Again, 3 significant figures is enough. 4 is a bit silly. 5 and more is really going to be wrong. Minus 22.16 kilojoules. Okay, so now we've got the units out of the way. Let's talk about, okay, does the negative sign mean it's wrong? Does the negative sign mean it's wrong? Does that make sense? Well, I'm not going to expect you to have an idea of what is 22 kilojoules okay for this kind of thing, because you probably don't even know what a kilojoule is yet. It's about the same energy as BTU, but I don't know if that means anything to you. But does the negative sign make sense? Well, look at the volumes. I'm going from a larger specific volume to a smaller specific volume at the same mass, so my total volume is actually decreasing. I'm going from a larger volume to a smaller volume. Hence the reason for the negative sign. You can see that mathematically, right? I've got this minus that. I get a negative sign mathematically. What is that telling me? Well, that tells me, sit all the way back up here. If I'm compressing the system, I'm actually putting work in. I'm going to get negative work out. And that's what we see here. I'm going from a larger volume to a smaller volume. I'm compressing the system. Therefore, I'm putting work in. I'm going to get, when I compute work out, and I know I'm putting work in, I'm going to get a negative sign. It's because the system's being compressed. That's a nice 15-minute video there. There's our answer. We'll pick up and move on to the next problem from there.